And today on the bench is a phono preamp from high-end audio designer Tom Evans. It's the Mastergroove preamp. It's very expensive and I've been told I won't be able to fix it. And here it is, the rather modestly named Mastergroove. Somewhat simple around the back, phono input and output. But we have got 24 mystery dip switches on the back. I'll have to see what that's about later on. I'm not entirely sure when this was made, but I think this dodgy logo dated a bit. Ripping off the Intel Inside logos. There's a bit of a backstory to this. This preamp's not very lucky, let's be honest. It started off with a 4-1 channel, buzzing, but then to add to its woes, the postman smashed it up. It looks very much like it's been bashed on this corner and it's smashed all this lid. And it's not little either, look how thick it is. 10mm thick perspex or something. And it also fails the rattle test. There's things rolling around inside. That's not encouraging. Let's check this out online, and this is from Tom Evans Audio Design, and it's a Mastergroove SR Mark III. Only 10 of these are made each year. Wow. This is basically a phono preamp, but it's for moving coil cartridges which have very low outputs. This is real high-end audiophile territory. It goes on to say, such is the overwhelming complexity and workload of hand measuring that perfectly matching every component of this ultimate phono stage, this limited edition model is only available at a rate of 10 units per year, featuring a custom case with fully balanced XLR output circuit as well as single-ended RCA phono output. Not this one. There's a lot of audiophile bragging rights going on here. Far more complex front end, 50% less signal distortion than the already referenced Mastergroove model. I'm not familiar with it, I have to say. This provides the greatest dynamic range of any phono stage in the world by an incredible margin. The new Mastergroove SR Mark III is quite literally beyond reality. And so is the price. Look at that. Well, who is this guy? Well, there he is. The genius himself, hard at work. Okay. Well, I do like the look of some of this equipment, especially this. Oh, and this. They're not very rare. I can't knock his taste in test equipment, that's one thing. Before I can test it, I've got to connect it to its power supply, which is rather large. My first impressions that this is somewhat overkill. It feels like there's a very big transformer in there for just powering a preamp up. So I'll just push this connector in there. I don't think it needs screwing in very much. Let's connect the oscilloscope to the output. See what's going on. Well, there's some funny stuff going on. We appear to have lost one of the traces. Oh dear, what is going on there? That is some big ripple. He's not kidding when they said buzzing. It's this channel. It seems to have settled a bit. Let's say we've got 2, 4, 6, 8 milliseconds between each one of those little peaks. That's about 125 Hertz. That's not mains hum, that's something else. Might as well disconnect all these now. So we need to have a look inside. However, its sleek black exterior has no screws. They must be on the bottom. Little ID label on the bottom, serial number 58. Must be quite an early one. Well, you know, in the 6th year. Rather optimistically, it's got lots of digits. This could keep him going for 100,000 years. Well, there's plenty of screws on the bottom, but none of them look like they get the lid off. Well, maybe I won't be able to fix it, I can't even get in it. Although I do wonder what these are hiding, because this looks like it's half off. I'm a bit worried about peeling it off a £20,000 piece of kit. Oh, there we go. There's a nut. Might as well peel them all off then. Just going to go with the 8mm socket. Well, the foot comes off. I assume this pushes up. I hope the bottom doesn't come off and leave the top on. Oh, oh, look at this. Oh, there's more braking parts here. That's not good either. Oh, a bit of machine feature. Oh, crikey, look how bent that is. Oh, it's spinning round. Oh. And the last one. There we go. I'm going to carefully flip this over. Let's have a look what's inside. There's quite a lot of stuff in here for a phono preamp, and the Royal Mail, they really have done a number on this, haven't they? Crikey. That's been booted across the car park, I reckon. These sides feel like they just lift out, and they do. Oh. We got bits of cardboard and broken plastic in here. Oh. Oh no, these are the plastic standoffs that are supposed to hold this all together. Parcel couriers got some explaining to do, haven't they? I think this big bulky post can come out, and the front can probably come out. Oh, it's got a wire on it. Okay, we'll lay it down. Well, reminiscent of a pair of multi-storey car park blocks, there's a fair bit of duplication here. These four boards look identical, and they look for all the world to be power supplies. We got the L7815 CV3 voltage regulator. Pretty common, nothing special about that. Oh, but hang on, what's this? That's not fair. Look, he's ground the numbers off. I hope he's not done that all over it. Oh, but he has. Look here. Oh dear, all these transistors. Or whatever they are. But again, we're seeing the set of four. Grinding the part numbers off is very old school, but it's still plain dirty. There's still not many clues what these things do, apart from there's only a couple of wires on, and I just wonder if it's more power supply stuff. There's a lot of copper shielding on here. I think these are just blank PCBs. It's quite a cheap way to do it. Quite smart, really. All got a ground wire soldered to them. Presumably they all go to the same ground, like a star ground. Let's have a look. There's various things going on in here. There's a lot of silicon with the part numbers hidden. He really doesn't want us to know what they are. We'll see if this one's the same. I have a suspicion it's exactly the same. It's interesting that this is a double-sided board and this is single-sided. Has that homemade feel to it. But yes, I think these two boards are identical, which leads me to conclude that all four are the same. I think this is only held on by the one screw. That's all that's left holding this. Yes. Oh, hang on, that's revealed another one of these boards. What are they doing with them? But we do now at least see a different board, this one here, which appears to have more chips with the part numbers ground off, but I'm going to guess they're op amps. I mean, it's a preamp. It must have them in. Oh, there's another one underneath. That's rather interesting. And I guess there's more of the same underneath. Yeah, it looks that way. I'm getting the impression this is built on two layers. Probably left and right. Or right and left, I haven't looked. Yeah, both these phono sockets go to this top board, which is the right channel. Okay, right on the top, left on the bottom. I shall check which channel was buzzing again, just to make sure. Sneak the power cable back in. There we are. Pull this one out, left channel, that's the one. Yeah, it's making no difference on the right. Let's measure the input voltage, red wire, 10.3 volts, white wire, minus 27. What's going on? Let's unplug this, see what's coming out of the socket. Let's put the negative in the centre, see what we've got. Minus 27, plus 27. Okay. So something's overloading the positive power supply rail and probably on the left channel. Trouble is, got to find it. Just a quick look at the wiring from here. The power comes into here, the plus and minus 28 volts I think it's supposed to be. These are all sort of joined together and they're distributed back to these boards. 1, 2, 3, 4. So H1, 2 and 3 are the inputs. So I'm pretty sure H7, 8 and 9 are the outputs. So this board here is supplying this blue board here, and these front boards are supplying these upper boards here. And you can see the same going on for the bottom part. And it looks like this op amp board's connected to this one somehow. And yeah, same going on underneath. Ah, right. Over here. Well, the power supplies are somewhat elaborate in this, and I'm not quite sure where it's all going, so I'm going to have to reverse engineer it, even if he has scraped all the part numbers off the things. But we can see in a £20,000 piece of kit there's a lot of labour going on here. I mean, if nothing else, the labour filing all these part numbers off must cost a fair bit. So I've now reverse engineered it and made myself a little service manual. I'm sure you'd like a look inside. Well, the first thing I managed to confirm was the layout. The top layer is the right channel, but the two are identical. The basic block diagram's pretty straightforward. The phono input goes directly into the low noise preamplifier, which is fed into an equaliser circuit, then through a low noise buffer and straight out the device. But in this design, they've done everything they can to keep noise right down to the minimum. The first thing to note is each active stage is powered by its own regulator. Each one of these are dual plus and minus 15 volt regulators. And these regulators are powered by their own regulators. How's that for thorough? And on the next page is the interconnection diagram, just showing how it's all wired together, pretty straightforward. Then we've got the power supply. There's nothing going to blow your socks off in here, pretty straightforward linear power supply with standard regulators. Moving on to the main board, which is the blue one. This is where all the action happens. And again you can see how the input signal goes directly into the preamp boards. Two of them. Then they go for this little filter for equalisation, and then to this op amp here, which is the line output. And what's interesting here is they're loading each one of these op amps with its own constant current source. At least that's what I think it is. And on the next page we look at the low noise preamp board. And what we're seeing are 4 identical op amp circuits, and each one of these has got a gain of 605. Now, whilst a lot of audiophile stuff is complete nonsense, there is at least some science behind this. Here's a conventional op amp circuit. This is the non-inverting one, so the input goes to the positive input. And on the negative input we have 2 resistors, creating a potential divider which creates the gain of the circuit. So you can put a small signal in, and it comes out the other side amplified. But what happens if you put a tiny signal in? Like for this phono amplifier, we are talking 0.4 millivolts. Which is certainly a tiny signal. But the op-amp circuit will amplify it in the exact same way. Apart from this time, we're going to experience a load of noise on there. This noise is actually coming out of the op-amp. The manufacturers will do whatever they can to minimise it, but it's very expensive to make low noise op-amps. And there are ways to improve it. And the key behind this is the fact that noise tends to be random. So if you look at this clever solution here, we take our tiny signal again, but this time we put it through 2 identical amplifier circuits, each one introducing its own random noise. If we then join these outputs together, we create a summing amplifier, which doubles the amplitude of the output, but reduces the noise level, basically because the noise is random, so when you add 2 random things together, they tend to cancel out. The noise reduction is proportional to the number of op amps in parallel. So if you're going to use 8 op amps in parallel, you reduce the noise by 2.83 times. It's very important that each one of these op amp circuits gives the exact same output, which is why the feedback resistors are a very high tolerance. Look at that, 0.1%. If you're to look at the datasheet for an op amp, you'll see lots of information. A lot of it is a bit confusing, some of it's very useful, the pinout for example, but we'll get to the important bit I want to show you now, the electrical parameters. We scroll down enough and we'll see we've got the input offset voltage, and it's something like 5 or 6 millivolts. Now consider that with a signal with an amplitude of 0.4 millivolts amplitude. You'll get some weird distortion in that circuit. And we start to see the reason for the manufacturer's claims here about all this hard work measuring and matching every single component. To measure the input offset voltage, the first thing we have to do is put the same voltage on both inputs. Because it's such a small measurement, we need to put some gain in here. So we can go with the 10 ohms at one side and 10k on the other. This will give us a gain of 1001. I built that circuit on the breadboard and I see what the offset voltage is of various op amps. I'm going to power them all with a plus or minus 15 volt supply. This is a UA741 op amp, and you can see the output voltage is 1.15 volts. That gives us an input offset voltage of about 1.15 millivolts. 1.15 millivolts, that's way too much for a 0.4 millivolt signal. I'm going to take that one out. I'm going to go with an LM308, which is about 0.2 volts, so that's 0.2 millivolts, which is 50% of the signal level. Pretty bad. I'm going to take that one out there. And next is an Analog Devices OP07. These are pretty good op amps. Now we're reading about 14 millivolts, which gives us an offset voltage of 14 microvolts, which is about 3.5% of the signal. I'd imagine for this preamp they're looking for input offset voltages of below 0.4 microvolts. That's about 0.1% of the input signal. That's going to be a lot of work. So now we understand it a bit better, we're well placed to start diagnosing what's actually gone wrong with this thing. Now if you enjoyed that little educational snippet, there's far more of this coming on my new training course I'm building for the Mend It Like Mark community. Check out the links in the description below. I'm going to start by removing the entire top layer, which is the right channel, because there's nothing wrong with that from what we can tell. I'm going to solder these sockets off the board. Start with the ground. They didn't put up much of a fight. Just unscrew these standoffs. They come off quite nicely. Need to undo this mess. Well, something's pulling the positive voltage rail down, which will be something that's gone short circuit, which is something that these little tantalum capacitors are very good at doing. And they're everywhere. But hello, I think we have a clue. That nylon nut looks pretty cooked to me, and that's IC5, and that is right at the beginning of the circuit. It's a 7818 regulator. A part he hasn't ground the numbers off, and that regulator board supplies this op-amp board here. I want to disconnect the output from this and see if the fault's just on the regulator board or outside of it. I need to get to the underneath. So I'm just going to unsolder terminal C. There we go. Put this back on there. Just set the power supply up for 28 volts. I'll give it a current limit of 0.5 amps. I'm going to need a common ground. Positive supply and the negative supply rail. Put a negative rail on there, positive rail here, and the ground on the black one. Power it on. Let's pick up the ground from here. Let's check the output voltage from this. There we go, plus 15, and over here minus 15. That's not great news, so there's a short on the fancy op-amp board. So I'm going to have to take this off again, so I need to remove the negative output, which is terminal E. So I can remove this off the 28 volt input, connect it to the supply to the op-amp board. But we need to change the voltage to 15 volts. And I'm going to knock the current down to 0.2 amps. Let's check we've still got the short. Oh yes, look at that. So I need to get this off. Just need to unsolder these wires as well. It's always slowest on the ground connection. There we go. That was hot. Let's have a look at it. Okay. Just going to remove this ground connection. It's going to be a bit more room. This board's actually attached by 8 wires down there, and that looks to be quite a nuisance to keep in line. So I'm going to unsolder this in one go, hopefully. I'm going to be using this 10mm blade tip. Get them all at once. Just going to flood it with a lot of solder. Make sure I've got good thermal contact. Should be less chance of damaging the pads. Just see if I can clean these up. and clean these holes out whilst I'm here. Well, that pin 4's not playing ball. I think it has got damaged. It looks like I've damaged the through hole plating. Now, I'm going to have to fix that because of the way this is all soldered together. Luckily I've got some rivets which are ideal for repairing this sort of damage. They're a little copper tube that's flared at one end. And the first step's rather painful. I'm going to have to drill that out. I'm just going to use a little handheld drill. So I'm now going in with a 1.3mm diameter drill. I'm just going to finish it off and open it up to 1.4mm. Just going to clean some of this flux off here. Just looks a bit of a mess. I should be able to just push this rivet in. Just rest it on this little base with a little recess in there and just press it down. And just flare it over a bit. And now just flatten it off. Just going to put a tiny bit of flux on there. And just run a little bit of solder under that copper rivet. So we've already established we've got a short circuit here on the positive rail. There it is, right here, 1.8 ohms. The problem is finding out which one, because there's a lot of things connected to this positive rail. All of the chips are on there, all of these capacitors are on there, could be any of them. So the quickest way to find the short is power it up and see what's getting hot. So with 200 millivolts we should start to see something getting warm. We've got some heat going on. You can see there the 4 chips glowing. And what is that on the top? That's a tantalum capacitor. And it's this one here, C12. We check where it is in the schematics. There it is. It's on the power supply for IC4. 10 microfarad tantalum cap. Well, it's interesting, it doesn't show any signs of thermal distress, but that's possibly because the power supplies near must be current limiting. Well, I don't think there's going to be anything fancy about this tantalum capacitor. Even in this, unless I've had it blessed by the Pope or something. You never know. I'm sure I'll have a tantalum cap knocking around here somewhere. Yep, here we go, perfect. So that should just drop straight in. There we go. Just solder that in. Get the ground on first. Takes a little time because it's got to heat up all of that copper surface area. And then this one. We'll just check if we got rid of the short. Well, that all looks pretty healthy to me. All the chips glowing evenly. And no hot tantalum caps. Just going to line these pins up. There we are. Well, that's typical where I put that rivet. There's no wire in it. Now'd be a good time to replace all these broken plastic bits. There's a little socket head screw in the bottom of here. There we are. I'll just unwind this. And put a new one on. And now's also a good time to reconnect these wires. Poke the white one in there and the red one in there. Always come out again. There we go. Just fasten this down to hold it still. Now I can pop that back on. Now it's a very good time to solder these connectors back on. This is the left input. And now the left output. There we go. Now it's a good time to test that left channel. Have I fixed it? Don't know why I plugged that one in. Well, that looks a lot more healthy, doesn't it? Just check this actually amplifying. Oh, look at that. I reckon that's good. Now I can put these standoffs back in. I've replaced the broken ones. Then put our shielding back on. This is probably to reduce crosstalk, I imagine. Then more standoffs. Got a snap screw thread in this one. I'm going to have to extract that. Although if it being plastic, just line a flat blade screwdriver up. Then heat it up. Just let that cool down. Let's just put the right hand channel back on. Bit of wires going everywhere here. Oh, and these 15-volt regulators don't sort of sit nicely. Just have to put the screw in. Just soldering the input socket. Just got to clean the end of this red wire up. It won't go in the hole. There we go. Put the supply leads back on here. Fasten this down with the standoffs. Oh, this is right, close to this heatsink. Can you hear it ratcheting on? Handmade machines, eh? That side's better. I can put the lids on these now. And the last one. In my excitement, I appear to have broken the ground off this one. Just strip a bit off. Just tin this wire. Heat this up. We'll remove the broken part. There we go. I should replace this cable tie before I put the sides on. Now I need to shim the joints for these bits of cardboard. Put one down there, one down the front, one in here, another one down there. I think there's room. Well, it's time for a test. I'm going to knock the amplitude down to 400 microvolts. Better do both channels, hadn't I? Let's connect the scope to the output. And connect our input signals in here. Okay, switching on. Well, there's signs of life. That looks pretty good to me. Same gain both channels, that's a good sign. Shows all those op amps are working. Now I've got to deal with this broken plastic lid. It's quite chunky and I bet it's quite expensive to make, so let's see if I can glue it back together. Start by peeling this off. Just spray on some label remover to get rid of this residue. It's like glass now. I'm going to put this waxed paper down on the bench so I don't glue it to the bench. That'll be a mistake. Put it face down when it's most flat. Now to glue this together I'm using this Trent Plastics Anglo-Sol. Recommended it works on this Perspex. If I'm right about it being Perspex. I'm just going to pull this crack apart here just so I can get the glue to run down in this little gap. I'm going to lay it down and put this clamp over it, just like that. And put some other glue around here. That's just easily just sneak in there. Then the same here. So if that's the wrong way around now. Pop that over like that. And put a clamp over here. And another one there. I'm now back in the old workshop because I do need to refinish this lid. So although the glue is set up nice and solid, it has leaked through here and marked the top surface, so I'm going to have to sort of sand all this back and repolish it. Luckily there's not too much of a step in it, but yeah, I'll have to get a little bit aggressive with this. Yeah, I've got to keep going until that's disappeared. It's nearly there. Now before I start polishing this up, I'm just going to fill these cracks with a bit of wax. Now these are designed for wood filling, I think, but I reckon they'll do if I can get it in the box. Use this black one. Right, it's ready to shine up. Let's give it a polish. Let's take this disc off and on with the pad. Well, that's not too bad for a glue job. I'm going to see if I can remove this all thread out of here. Stick it in the vise. Success! Just screw this in. That'll do. Just going to blend off some of this paint so I can just refinish these little chips. That looks okay. Feels nice and smooth. I'll put some paper over here to protect it from the paint. I'll start with some etch primer. Just let those dry overnight. Just reattach the feet. And this clamps the whole case together. Just need a bit of light adhesive to glue these felt pads back on. Let's tip this over so the weight of it holds the pads in place. Looking nice now. I don't know about 25,000 quid though, but yeah, it's looking okay. Okay, it's ready for one last test. Let's connect the scope. Now I have managed to bag a record player to test this with, but it's got a moving magnet cartridge. So I need to use these attenuators just to knock the level down. This trusty old biogram. The workshop on this on the Mend It Like Mark community. You'll see all the information about this and the links in the description. But how much do you think the manufacturer would have charged for this repair? Leave your answers in the comments below. Catch you next time. But it feels like Elvis is in the room with me.